Okay, so now that we know some things about atoms, we're going to talk a little bit about ions because they are derived from the different types of atoms. By definition, ions are just atoms or groups of atoms that have a net positive or negative charge. The positive charge results when there are fewer electrons overall than protons. For example, if you have a sodium atom, it has 11 protons and 11 electrons, so they're the same. But a sodium ion, notice that it has a +1 charge. So that means that it has one extra proton. There are still 11 protons. That's what makes sodium sodium, the number of protons. But in order for it to get that positive charge, it has lost an electron and now it only has 10. So that's what this little picture is meant to represent. You start with a sodium atom, it loses an electron and becomes a sodium +1 ion. Now, the name for positive ions is cation. Negative ions are those with negative charge, and that results when you have extra electrons. You have more electrons than protons. So for example, chlorine atoms have 17 protons and 17 electrons. The chloride ion, and we'll talk about the naming conventions later, but when you make a negative ion out of chlorine, it's called chloride. It has 17 protons. Again, it has to have 17 protons because that's what makes chlorine chlorine. But that negative charge means that it has gained an extra electron. So now it has 18 electrons. So again, here's a little picture of what's going on. You start with the chlorine atom, you add an electron, and you get a chloride negative ion. And negative ions are called anions. So something that people often use to remember the definition of cation and anions. Cations, they're positive. They're like cute little kitty cats, right? And the eyes kind of look like plus signs, I guess. And then onions sounds kind of like anions, and onions are negative. They make your eyes hurt. They make your eyes water. So it's like your eyes are closed. So they're kind of like negative signs, right? So anions. So, judge for yourself whether or not that's a useful tool to help you remember the definition of cations and anions. So these ions will work together to form compounds, and they're called ionic compounds. These are compounds made of ions. And the tip you can rely on to always identify an ionic compound is that it will have a metal in the formula, with a few rare exceptions, but in chemistry, there's always some rare exceptions. But that's how you identify an ionic compound, if there is a metal in the formula. So there is that transfer of electrons that we talked about in the previous slide, sodium losing an electron, chlorine gaining an electron. But these ionic compounds can be said to be compounds that are made of ions that are formed by that transfer of electrons to or from atoms. Why does this happen? Why would something lose an electron, or why would an atom gain an electron? Well, this is done in order to gain some stability. So the stability that atoms are looking for is a full valence shell. So for many elements, this full valence shell is going to be 8 electrons. And so you may have heard of this before in a previous science class. This is called the octet rule. Atoms will gain or lose electrons in order to get 8 in their valence shell, their outermost shell, and we call that the octet rule. So here's an example. We'll go back to the sodium. So we said that sodium atom has 11 protons and 11 electrons. And so if you write out the electron configuration, then you'll see that its valence shell is the third shell here, right? So those are the valence electrons. And notice that there's just one valence electron. Well, if it gets rid of that valence electron, then it will have a full outer shell, because this is the electron configuration for sodium +1 ion written right over here. It has 10 electrons. And so if we get rid of that 3s1, what you're left with is a full second shell. Okay, 2 + 6 is 8. It follows the octet rule. Okay, there are 8 valence electrons. So that's generally what atoms will do, is they will gain, or in this case, lose electrons to get that full outer shell, which for many elements will be 8 electrons in the valence shell. Now, of course, there are exceptions, and we want to point those out. Hydrogen and helium, they only want and need 2. to have a full outer shell because they're so small. So they don't obey the octet rule. They're happy with either 0 or 2 in their outermost shell. And then with transition metals, it gets more complicated, and we don't really get into that in this course. For a lot of them, it's 18. And so there is such a thing as the 18 electron rule, but you don't need to know that for this course. And I'm just mentioning it so that you know that all those metals in the middle of the periodic table, they also don't follow the octet rule. All right, so once we create these ions, they are held together into compounds by these attractive electrostatic forces. You're familiar with, the phrase opposites attract. So you've got positive ions and negative ions, and they're attracted to each other in a given ratio, and that's what forms the compound. And that type of bond, that attractive force, is actually what we know as an ionic bond. In the strict sense of the word, it's not a bond, but because it holds these ions together, it's called a bond, and it's an ionic bond. Okay, so what this does ultimately is it forms a crystal, a three-dimensional lattice of positive and negative ions. It looks like a framework, a skeleton, so to speak, and we would commonly call those crystals. And so the next slide shows you what I mean by that. So the example would be something like sodium chloride, table salt. And so because of these attractive forces, the positive attracted to the negative, and so you can see it sets up a lattice like this framework. And that's a crystal structure. And on the macroscopic scale, if you could grow the crystals large enough, they would look kind of cubic. This looks somewhat like a cube. But you can see this has cubic nature to it as well on the large scale. All right, now, as I said before, the way to identify an ionic compound is because there's a metal in the formula. So we could put that in the notes as just this general rule that ionic compounds are often made of metal ions and non-metal ions.
Holy heart failure!
Okay, now what you need to know is what charges form on the ions based on their position on the periodic table. So charges on ions depend on the location in the periodic table. And you can kind of see those listed out in this periodic table. The reason why I put that sound effect in there, the holy heart failure, because I don't expect you to memorize all of these possible charges, but there are some that you can memorize fairly easily and quickly based on the column, based on the group. So notice that the column will dictate the charge, +1. It's in column 1, it's in group 1, and they like to form +1 ions. It's in group 2, they like to form +2 ions. Over here in group 13, they like to form +3. And then in 15, it's -3, and then 16, it's -2, and then 17, it's -1.
Have a look at this.
So if you remember that, then there's very little memorization actually involved. The elements in these groups like to form the same type of ions. And as you can see, that the metals, the things on the left of the periodic table, like to form positive ions, and the non-metals, those on the right, like to form negative ions. Okay? And as we go back to what we learned in previous lessons, the reason why they adopt these charges is to get that full outer shell and obey the octet rule. Okay, so the one thing that is also important to notice is that hydrogen, we said earlier that non-metals like to form negative ions. Well, an important exception is hydrogen. Hydrogen likes to form a positive +1 ion. Now, these come together to form ionic compounds. So how do they do that? Well, they're going to do that, and you can come up with the formula of that compound when you establish the smallest ratio where those ions neutralize each other. In other words, they reach a net charge equal to 0. So for example, when magnesium +2 ions come together to form a compound with chloride ions, Cl-, it requires 2 of those Cl-. So the formula would be MgCl2. The 2, that subscript 2, represents the number of Cl- ions that are present. So the reason why it takes 2 Cl- is because of that +2 charge on the magnesium. So that +2 charge on the magnesium ion is going to be neutralized by the negative charges on 2 Cl-. Okay, so overall +2 on the magnesium, and an overall -2 from the chlorides, because each one of them carries a -1 charge, and there are 2 of them. And as I said, the subscript in the formula indicate the number of each ion. Here's another example. So if the formula is Na sub 2 S, what that means is that there are 2 sodium ions and a sulfide ion, 1 sulfide ion. Again, remember that in chemistry, ones are implied. We don't do ones for subscript, superscript, coefficient. Ones generally don't show up, but they are implied. So there are 2 Na plus and 1 S2 minus ions in the formula unit. Okay, so now here's another typical question you might be asked. So what is the formula of an ionic compound formed between lithium and nitrogen? And so think about the periodic table and where these things show up on the periodic table. So let me find my periodic table here and drag it over. So lithium is in group 1, so that means that the lithium likes to form a +1 ion. Right, so here's lithium, and so lithium likes to form a +1. And then nitrogen's right here, so it's in group 15. So again, you memorize, or you can kind of go over. These like to be -1, these like to be -2, these like to be -3. So the nitride, the nitrogen ion is going to be an N3 minus. Okay, so the ions I've got to work with here are lithium plus and N3 minus. Okay, so let's talk about how to make a compound with those ions. So because lithium is in group 1, it likes to be a +1 ion. And because nitrogen is in group 15, it likes to be a 3 minus ion. So at this point, the net charge is going to be -3 + 1, so it's still going to be -2. Okay, so it's not 0, and that's what nature wants. Nature will establish this ratio of ions in order to get a 0 net charge. So we're not there yet. A 1-to-1 ratio doesn't get us there. I'm still negative, so what I need more positive. So maybe 2 lithium ions will get it done. So now I've got 2 lithium ions, so Li and Li plus and Li plus and N3 minus. Well, it's still not neutralized yet. I still have -1 overall. 2 times +1 -3 is -1, not 0. And that's with the 2-to-1 ratio. So you can see where this is going. So if I throw in another lithium +1 ion, then I get 3 positives and 3 negatives. So it achieves that 0. So it's that 3-to-1 ratio that achieves that overall neutral state. And so my formula is going to be Li with a subscript 3 to represent 3 lithium ions and then the 1 nitride ion. And again, I said nitride, that's the ion's name. I'll talk more about the naming rules in just a little bit. All right, so there is a very simple technique that we can use to come up with these formulas based on the charges, and it's called the crossover technique. So the magnitude of charge on each ion becomes the subscript on the other ion in the formula unit. That's the key. So for example, if I have these 2 ions forming a compound, I have an iron 3+ and an oxide, oxygen 2-. So the superscript on one will become the subscript in the formula of the other. That 3 is going to become a subscript on the oxygen, and that 2 is going to become a subscript on the iron. So the formula of the ionic compound formed between iron +3 ions and oxygen 2- ions, also known as oxide ions, is Fe sub 2 O sub 3.
Okay.
Now, there is, of course, always one complication that you have to keep in mind, is that sometimes this ratio isn't the lowest possible ratio. So you, in some instances, we'll need to simplify it to the lowest whole number ratio. Here's an example. So if I do the crossover technique with copper 2+ and sulfide, you'll see that it would mean I would have, think about the crossover technique where that 2 becomes a subscript on the sulfur and that 2 becomes a subscript on the copper. Ugh, my penmanship is really bad, apologize. This is not as simple as it can be. So you reduce those by just, dividing both of them by 2, and you get the lowest ratio, 1-to-1. So the formula of the copper sulfide ionic compound would be just CuS. All right, so I promised we talk about naming, so here we go. So how to name these ionic compounds according to the IUPAC rules. Now, the IUPAC is just an acronym for the International Union of Pure and Applied Chemistry. They're the folks that get together and set the rules for a lot of different things. So the first element in the formula is the cation, and that's easy. You just name the element. And then the anion, if it's a monatomic, or let's say this, the mono element, so if it's one element, then you just change the suffix on the element to ide, IDE. So for example, chlorine becomes chloride.
You got it.
And so MgCl2 would be called or named magnesium chloride. So the cation, which is magnesium, you just say the name of the element, magnesium. And then the anion, you take the root word, which is the elemental name, chlorine, pardon me, and then you change the suffix to IDE and it becomes chloride. Okay, so there are more complicated rules when you deal with the elements in the middle of the periodic table that don't faithfully adopt a single charge. So we already talked about how the groups on the extremes of the periodic table, you pretty much know what charge they're going to adopt because they follow the octet rule. But those guys in the middle, which is again beyond the scope of this course, and you don't really need to know how and why they adopt the different charges that they do. But because of the fact that they can adopt multiple charges, we have to have some special rules for naming compounds that include these elements. So there are special rules for naming compounds with metals that can have multiple charges. So here they are. So we employ Roman numerals in parentheses to indicate the charge on that cation. So the name of the cation is the name of the element with a Roman numeral in parentheses equal to that charge. So once again, let's do some examples to show you what I'm talking about here. So if it is a copper +1 ion, the name would translate into the name of the element, copper, and then in parentheses, we would put a Roman numeral for the charge. So this +1 becomes a Roman numeral 1 in the parentheses. But copper can also be a +2 ion. Huh? And so its name would be still copper, so that hasn't changed, but the parentheses have a Roman numeral 2 inside because this is a 2+ ion. So if we were going to name this compound CuCl2, remember that you can, or what I recommend that you do is kind of reverse engineer the formula to get the charge on the positive ion. So this 2 was a +2 charge on the copper, right? So you reverse engineer that to come up with the actual charge on that copper ion. And so then, because you know it's a +2, then you use the copper with the Roman numeral 2 in the name of the compound. And then the anion is no different. You just, no special rules for the anion, just the chlorine becomes chloride. So there are a few elements that don't follow this rule. I know I keep saying that. This is just one of the things about chemistry that you just have to deal with it, but I don't want you to worry about it. And those elements are typically zinc 2+ and silver +1. So they won't necessarily have a Roman numeral with an in parentheses. And that's because for whatever reason, again, beyond the scope of this course, zinc does not form, pardon me, getting tongue tied. Zinc does not form ions, multiple charged ions. It faithfully forms just +2 ions. And the same thing with silver, it faithfully forms only +1 ions. So there's just no need for this system of naming for those two. And there are a few other ions that are like that. But the big thing to remember is it's never wrong. It would not be wrong to say, for example, it would not be wrong to put this as zinc with a Roman numeral 2 in parentheses in a name. Like if it was zinc chloride, you know, zinc parentheses Roman numeral 2 chloride. That is acceptable, but you could also just put zinc chloride because zinc always forms a +2. But either way is acceptable. But I really want you to focus on the normal scheme. Don't worry so much about the exceptions to the rule. Okay, so let's do some more practice, putting all this together. So here we've got some formulas and we want to write the name. So K, that's potassium, and remember, so that's the cation, that's the positive ion. And remember that you just, write the name of the element for the cation, potassium. And then the fluorine becomes fluoride. So Fluoride. So fluorine becomes fluoride. All right, so this one right here, I recognize that that is in the middle of the periodic table, so it can adopt different charges. It might be +2, it might be +3. So the way in which I come up with the charge in order to name it correctly is, again, you can kind of reverse engineer it. The subscript 3 was once a charge on that iron ion, so it's a 3+ ion. So this is Fe is iron. So iron, and this was a 3+ ion, so I put in parentheses 1, 2, 3, Roman numeral 3, and then once again, chlorine becomes chloride. Okay, so the formula going from the name to the formula. Well, the zinc, as I said in the previous slide, it faithfully forms a +2 ion. So that's the ion that's involved. In nitride, because of its position on the periodic table, I know it's a -3. So if I just use the crossover technique, okay, so this becomes zinc with a subscript of 3 and nitride with a subscript of 2, or nitrogen with a subscript of 2. And the other way to think about it is this is 3 times +2. So overall, that's a +6. And this is 2 times a -3. So overall, it's a -6. That's the way you get it to be neutral. And then copper 1 oxide. Well, copper 1 is just the C with a plus. And then oxide, because of its position on the periodic table, I know that's a 2-. So using the crossover technique, that 2 becomes a subscript on the copper. So its formula would be Cu subscript 2 with an O. Potassium fluoride, iron 3 chloride, Zn sub 3 N2, and Cu sub 2 O. All right, so one more curveball to throw at you here is that there are some ions that are not monatomic. They don't include just one atom. They include multiple atoms that are connected together, and they share a charge. So these are called polyatomic ions. So they are a group of connected atoms that share a charge. And so here's a list of them. They have a name, they have a formula, and they have charges. All right. So what I mean by atoms connected together, we'll get more into this in lesson 4, but they have bonds between all the atoms. So the sulfur is connected to, it's bonded to these 4 oxygens. And overall, as a unit, it has a -2 charge. That's sulfate, for example. Now, the bad news is,
Oh no, we're all doomed.
this is chemistry, right? So there's some memorization. I do need you to memorize these polyatomic ions. So I would recommend making flashcards, and you put the name on one side and the formula with the charge on the other side, and then just work through them until you get a handle on them. Now, the good news is really, if you do enough practice problems, it just kind of sinks in, and you won't have to spend a lot of time memorizing them with flashcards or a list or anything like that. But unfortunately, there's no way around it. This is just one of those things that we do expect our introductory chemistry students to learn, is the names and formulas of the polyatomic ions. And so one more thing to point out over here is that the acetate ion will be represented with 2 different formulas in different resources, different textbooks, different YouTube videos, whatever. So I will typically use this one, C2H3O2, and it has a minus charge. It's called acetate. But other resources will have it written this way, CH3COO minus. Okay, so just be aware of that. Both of them are the same thing. They're both acetate. Okay, so let's do some practice with these polyatomic ions. So in this situation, we want to write the formula unit and the name for these combinations. All right, so for this first one, we can just do our crossover technique, and this +1 becomes a subscript on phosphate. This right here, you have to memorize, is called phosphate. Okay, and this 3 becomes the subscript on the sodium. So the formula would be Na subscript 3 and then PO4. And the naming rules are the same. It's just that I have to utilize the name of the polyatomic ion. So this would be sodium phosphate. All right. So next one, calcium ions and nitrate ions. Well, calcium ions, I know that they are Ca2+, and I know that because this is in group 2 of the periodic table. It's in that second group, second column of the periodic table. So it likes to form +2 ions. Now, nitrate, you just have to memorize. It's one of those polyatomic, and it's NO3-. It's got a -1 charge. So if we use the crossover technique, the 2 becomes a subscript on the nitrate, and the 1 becomes a subscript on the calcium. And so there's a little trick to writing these. So the calcium is going to have a subscript of 1, so that's implied. But this nitrate, the whole unit of NO3, gets a subscript of 2. So I use parentheses, NO3, it goes in parentheses, and then I put the subscript 2. All right, so the name of this would just be calcium, just name the element for the cation, and then I memorize this is called nitrate, so it'd be calcium nitrate. Okay. All right, so finally, So ammonium, this is another one of those polyatomic, and this one is somewhat unusual because it is a positive polyatomic ions, NH4 plus, right? There's just a couple positively charged polyatomic ions that freshman level chemistry classes generally use. The other one is hydronium, H3O plus. Ammonium is the other, NH4 plus. And I remember that sulfate, or it's given that sulfate is SO4 2 minus. Okay, so this becomes a subscript on the sulfate, and that 2 becomes a subscript on the ammonium. So here, the subscript of 2 has to apply to the whole formula for ammonium. So we go NH4, and then I put that in parentheses and put the subscript of 2. And then the subscript of 1 goes on the sulfate. So I could just write that SO4, okay? And then the name would just be ammonium sulfate. Okay. All right, so this is another one of those exceptions to the rule that I mentioned earlier. This is an ionic compound without a metal in the formula. Notice all these are nonmetals, a non-metal, 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 but because these are ions, it is composed of ions, this positive ion and this negative ion, that's what makes it an ionic compound. So earlier when I said you can identify an ionic compound by the metal in the formula, but here is one of the few exceptions to the rule. Whenever there's ammonium ions involved, it acts like a metal ion. It is a cation that's composed of all non-metal elements. So just remember that. The other thing I want to also say in this set of examples is that notice that in these formulas that we wrote, these are the correct formulas for these compounds. There are no charges listed. You don't put charges when you're writing the formula of the compounds. Okay, you might see when you're writing the individual ions, they should have charges. These individual ions have their charges. But when you put them into a compound and write out the formula for the compound, then you don't include the charges. And I notice that students are make that mistake fairly commonly. They might try and keep that 2 plus there in the formula for the compound, but you shouldn't do that. All right, so Na3, PO4, sodium phosphate, calcium plus 2, and the nitrate minus the crossover. So we use the parentheses to put the subscript 2 around the whole nitrate formula, and we call it calcium nitrate. And so ammonium sulfate, same thing. That 2 becomes a subscript on the ammonium, so that the parentheses are needed in the formula, and the name is ammonium sulfate.
Now it's your turn.
Okay, so we're just going to do some more of these. Practice makes perfect. So the name for this formula, okay, so I just need to look at the periodic table and see what the name of this element is, because that's how you start the name. And this is called vanadium. So vanadium. And so then the ClO2 is right here, ClO2 minus, right? Okay, and we reverse engineer this. So this 3 was a charge on that vanadium, so this was V3 plus. So that means this, vanadium is in the middle of the periodic table. It's a transition element, and so since it can have multiple charges, I need to put that charge, that Roman numeral 3, in parentheses in the name, and then this is called chlorite. ClO2 minus is chlorite, so I just put that name here. So vanadium, Roman numeral 3, chlorite. Vanadium 3 chlorite. Okay, so lithium cyanide. So lithium, I know is in group 1 of the periodic table, so it's going to be a +1. And the cyanide, that's a polyatomic that you just memorize, and so it has a formula of Cn minus. And so I use the crossover technique, and this one has a very simple 1-to-1 ratio. So the formula would just be LiCn. Okay, and calcium hydroxide, calcium is +2, and hydroxide you memorize. It's another one of these polyatomics right there. Oops, it's a -1. So the crossover technique, so its formula is going to be Ca, and then I use parentheses because that 2 applies to all of it. So Ca parentheses OH sub 2. Okay, vanadium 3 chlorite, LiCn, Ca parentheses OH sub 2.